Thank you very much. Thank you to the organizers for inviting me here. I'm sorry to be one day late because of teaching yesterday. So I'll be talking about quantum magnonics with synthetic antiferromagnets. A large part of my talk will actually be introducing synthetic antiferromagnets, which I think, connecting to the previous talk, are actually a nice example of a platform with which to realize many of the things that we heard in a more general context in the previous talk. So just to introduce the people who are involved, so the work I'll be talking about has mostly been done by former PhD student Joran Harms and current PhD student Artem Bassin. Valentina Rani is in the room on the back. I will not be talking about her specific work, but she has done similar stuff on antiferromagnets. So if you want to hear more about it, please talk to her. The postdoc involved, the driving force there was Weiyang Zhuan, who is now back in his home country, China, as a faculty. So just to give a broader context, I'll be talking about, so the context is spin waves. We're doing stuff with spin waves, and the application-motivated field that does that is called Magnonics. So here's an example of a spin wave. They were introduced this morning already by Amir. So it's an elementary excitation on a classically ordered magnetic ground state. So the simplest case is just a homogeneous ferromagnetic state. Then we have these wave-like precessional excitations. And if you want to do useful stuff with them in terms of next generation, let's say beyond more devices, so they're attractive because there are no ohmic losses for spin waves, no electrons moving. They can be relatively fast, so we're thinking about gigahertz frequencies here, or for antiferromagnets even terahertz. They have a phase and amplitude. Magnetic systems in general can be very nonlinear. And more recently, they've also been pushed into the quantum regime, in particular in studying the interaction of spin waves with superconducting systems. So if you want to read more about, let's say, the general field of Magnonics, I advise you to check out this roadmap. Andre in the back, and I think Benedetta are involved with this, and maybe more in the audience. And there's also a nice review on, let's say, the quantum efforts in this direction that you may want to check out. It's in Physics Reports. So I'll be talking about very basic systems, so it will actually be technically relatively simple what I'll talk about. So these are synthetic antiferromagnets, so they are basically magnetic layers. For most of the talk I'll be considering single domain magnetic layers that are, let's say, are Lego pieces in some more complicated stack involving also non-magnetic layers. So a typical example is this one, where you have two ferromagnetic layers that are coupled through a non-magnetic spacer. This mediates an RKKY type coupling. In this example, the magnets are in plane. They can be out of plane, or you can put more than one, and you get this magnetic multi-layers. So these kind of structures were very crucial in discovering giant magnetoresistance, which kickstarted to a large extent spintronics. And they're kind of easier to work with than crystal antiferromagnets, because you can basically, because of the larger scale, manipulate both magnets separately. So the setup that I'll be talking about most of the time is just a bilayer. So we have two single domain magnets. Later on I'll extend to inhomogeneous situation, two single domain magnets that are coupled through some magnetic spacer in one way or another. I'll elaborate on that in a second. And the individual classical dynamics of the system is described by the Landau-Lipschitz-Gilbert equation. So there's an equation for the direction of magnetization. So M1 and M2 are the direction of magnetization of these magnets. So these are just magnets well below their Curie temperature. The only degree of freedom is the direction in which they point. And that direction can classically precess around an effective field, given as a derivative of some energy that I'll specify later on. And there's a damping term, a viscous damping term, due to dissipation of spin angular momentum and energy into the environment of the magnet. This is called the Gilbert damping term, and typically in magnets is due to coupling to the electronic reservoir, and in insulators it's basically due to coupling to lattice vibrations, phonons. And so the magnons in the single domain case will just be the quanta of h bar of the homogeneous precession of the magnet. So if you linearize this dynamics, you can basically replace deviations from the z direction, which is the quantization axis in our case, and quantize them to promote them to be bosonic operators. Okay, so just to give you a bit of a feeling for the type of interactions and how to tune them. So a very common interaction that we consider is an interlayer exchange interaction. So you place two of these magnets as a sandwiches between some piece of cheese, say, in the middle, and that, let's say in the case it's a non-magnetic material, this will mediate then interlayer exchange coupling, commonly referred to in the case of metals as RKKY coupling. And this is due to the, let's say, the magnetic moments polarizing, spin polarizing the electrons at the Fermi C in the non-magnetic spacer, and basically leads to a standard isotropic, in the simplest case, exchange interaction, which just favors alignment of the two magnets. But what is important here is that this interlayer exchange interaction is strongly distance dependent and oscillates with distance. So by choosing the thickness of this spacer here, this layer in between the two magnets, you can make the interaction either ferromagnetic, favoring parallel alignment, or antiferromagnetic. Now, very recently, it was shown that if you have sufficiently strong spin-orbit coupling in this non-magnetic material and you break some symmetry, for example, by drawing it in a specific direction, that you can also engender a Dzielinski-Moria interaction, an interlayer Dzielinski-Moria interaction that basically mediates a coupling of this chiral nature. So you get a chiral interaction parameterized by some vector d that depends on the specifics of the material that's being sandwiched between these two magnets. Okay, so these are two typical coherent interactions that we can have. Go ahead. So I'm really thinking about, for the moment, about single domain magnets. So if you do something to the left magnet, it will precess homogeneously, and it can then, okay, do something to the right magnet via coupling. But I'm not looking yet at, let's say, wave-like excitations. Does that answer your question?
Yeah, yes.
Okay, so these are two examples of coherent couplings that we can have. Now, isolating now on one of these magnetic layers, what is also possible is to actually inject or extract angular momentum electronically. So if I look at this single domain magnet here, if focusing on this left non-magnetic layer, so if I place a heavy metal layer on top of it and I run a tangential current to the interface, then if it's a heavy metal, there will be a large spin-orbit coupling leading to a spin-hole effect, which leads to a transverse spin current, so flowing in this direction. And this transverse spin current can flow across the interface between non-magnetic heavy metal and the magnet. And this can then, via spin flip scattering at the interface, dump angular momentum in this ferromagnet. So that leads to, well, what people refer to nowadays classically as spin-orbit torques. So these are torques of extra torques of this form on the magnetization dynamics. And what is important for, so I don't want to go too much into detail of this spin-orbit torque physics, but what is very important for this presentation is that this leads to a anti-damping torque, meaning this is a torque that can compensate if the current is flown in the right direction for the dissipation of angular momentum. So it can basically compensate the Gilbert damping. And physically this is kind of clear because Gilbert damping leads to dumping of angular momentum away from the system, and this, for the right sign of the current, can lead to injection of angular momentum. Now the reciprocal of this is that this magnet which is precessing can also emit spin current via a process that's classically called spin pumping. So that leads to a current that's pumped So in this case, I've drawn it on the right. So if this magnet is processing, it will pump a spin current into the adjacent normal metal. The spin current is of this form. And this is basically the reverse process of the spin-orbit torque, the reciprocal process of the spin-orbit torque. Now this is kind of the classical picture or the classical physics. So quantum mechanically, it's better to think about modeling this in terms of electronic reservoirs or spin reservoirs for the magnons in the ferromagnet. So what we often do, and you can kind of derive this starting from this classical picture, well, not kind of derive this, you can derive this from this classical picture, is that if you look at magnons, for example, the magnon occupation of this magnet here in contact with this heavy metal that's driven, you can basically model that as a spin reservoir at some chemical potential that is determined by the amount of current that you drive, and that reservoir then starts occupying the magnons and basically drives the system out of equilibrium. Good. Now, the final ingredient that I would like to advertise is that the combination of this spin transfer physics and this spin pumping physics leads to a non-local coupling between two magnets, meaning that if this left magnet processes, it can emit a spin current that is drawn here in this intermediate spacer. It can emit a spin current via this spin pumping physics. And then this spin current can be absorbed by the other magnet with this spin orbit or spin transfer torque effect. And this can basically mediate a dissipative coupling between the left and the right magnet. So it can lead to basically the combined effect of these two processes, so emission of spin current and absorption of spin current, leads to a non-local damping term, at least if you write it down classically, leads to a non-local damping term, which is of the form of an ordinary Gilbert damping term, but involves basically the dynamics of both magnets. Now, if you write this down after Holstein-Primakov transformation and so on and so forth, and choosing the resonant energies, this will basically be an imaginary hopping of magnons from left to right magnet and vice versa. And so a lot of this, this dissipative coupling can be used to engineer, or basically to engineer neat non-emission physics for magnon systems. Okay, let's see, where is my timer? Good. So I want to now give basically two examples of doing something with these interactions, something fun from the point of view, and perhaps something useful even from the point of view of quantum magnonics. So the first one being using the coherent interaction and incoherent interaction, so the dissipative and coherent interactions, in such a way that you get a unidirectional interaction and possibly get a magnon diode, a spin current diode, and the second one being going to an out of equilibrium situation to create entanglement between magnons. The second example I'll be, well, actually both examples, but specifically not technical about, because the next speaker will give a more in-depth discussion of that and also some more in-detail applications. So let's first go to the first bit. So what we now have in mind is, again, this simple setup. First looking at classical dynamics only. And looking now at a coupling between these two magnets, which is not of the exchange type, is only chiral and is only dissipative. So I only have two terms that I mentioned previously that couple these two magnets. One is the interlayer Dzielinski-Marie interaction, this chiral interaction. The other one is this non-local pumping, so this non-local damping that couples the two spins, two magnets dissipatively. Now, choosing then the external field H and the Dzielinski-Marie vector in the same direction, let's say the z direction, you can write down these two classical equations of motion for left and right magnet, M1 and M2. You get these equations, so there's a term due to the DMI, there's a term due to the external field, and there's this non-local coupling, and I've not written down the local, so this non-local damping, this viscous coupling, dissipative coupling, but I've not written down the local Gilbert damping because it plays no role for what I'm going to say. Now, what you can see is if, well, the first observation is that this non-local dissipation, this parameter here, which is dimensionless, this non-local Gilbert damping parameter, is typically very small, let's say on the order of a few percent or even much smaller. That basically allows you to solve the equation iteratively, order by order in this alpha. And basically what you can do to lowest order is just replace the mdt in this damping term then by the coherent part here. So that leads to this replacement, and then you get these two equations of motion. The reason why I am so elaborate about these technical steps is that these are the only ones I did in this project myself, so I can, you know, when I start skipping details, you know that I don't have a clue. Okay, that's maybe... anyway, so then you get these two equations, and what is now important, or nice, I think, is that by choosing the field appropriately, you can basically take this non-local damping torque and let it precisely cancel this term or this term, but not both at the same time. Meaning that if I choose h to be, let's say, minus d, I cancel it in the lower equation and not in the above equation. And what you then get is a situation that by basically you get into, let's say, phenomenologically into the situation that the dynamics of the, in this case, right magnet, so M2, it actually influences the left magnet, but not vice versa. And so if you tickle the, let's say, the left magnet, it will not affect the right magnet, but vice versa it does. And if you reverse the field, the situation is precisely the other way around. So the unidirectional coupling, as we like to call it, is precisely the other way around. And so what happens is that we have balanced now this chiral coherent interaction precisely with the dissipative interaction, and this occurs for specific values of the field where you choose the field to be this value related to the Dzielinski-Maria vector divided by the non-local damping and some constants. So based on this, you can build a spin current diode where if you now connect the system to leads, to reservoirs to drive spin current from left to right, if you do the computation of the spin current, let's say out of this reservoir and into that reservoir, you get a Landau-Büttiker type expression determined by the difference of the occupation numbers of the spin in left and right reservoir times some transmission probability, and this transmission probability is basically is not zero for left to right, depending on the sign of the field in getting this unidirectional coupling, and is zero for the propagation in the other direction. So I actually I didn't put any, I've cut out the plots of this transmission function. So this transmission function is given in terms of a Fisher-Lee-like expression in terms of the scattering rates in and out of the reservoir and the Magnon-Green's functions. I cut it out because I saw the previous speaker getting out of time and I was scared for myself as well. So I was cutting like crazy during your talk. But anyway, so this basically gives a perfect spin current diode, and it's only perfect, of course, if we ignore the interlayer, ordinary interlayer exchange coupling. So what you can show is that if you start increasing that, then the perfect diode behavior is gone, but it still works pretty well. So this may be a nice, and a possible application of this would be to kind of read out Magnonic quantum states without any back action. Now, just to connect this to some work that I think some of you probably know very well. So this example that I showed is a specific implementation of the idea that is kind of advocated in this paper, is that it's always possible when you have coherent interaction and dissipative interactions to balance them in one way and not balance them in the other way. And so basically in our case, the coherent interaction, as I emphasized, is this chiral coupling, the DMI. And here they talk about, in this paper, they talk about these dissipative effects in terms of 5 minutes. Did you say? 5 minutes? No, I don't know if you, I thought you, I saw you from my, I thought you gave me a sign, but it was all over interpretation of some movement in that. Anyway, so in this article, it's kind of, this dissipative coupling is framed very much, or is phrased very much in terms of specifics of the reservoir, and it's dubbed reservoir engineering. So in our case, the reservoir are basically the electrons that mediate the dissipative coupling between the two magnets. And so for most of the applications in magnetism, the magnetization dynamics is so slow compared to the electronic timescales that it's not needed to worry too much about the electrons to lowest order in frequencies and so on. But I think this also gives like a way to think about forward perhaps with these kind of systems. And so right now we're kind of trying to put these ideas that that I just described also on a little bit more quantum footing by treating also the electrons quantum mechanically. And I believe Benedetta also has works about that, relating, for example, Gilbert damping to Lindblad type equations and whatnot. Okay, so that was one example. The other example I would like to discuss is an out of equilibrium example. And as I said, this will be discussed also in more detail towards the end of the next talk. And so I'll be relatively brief. So now we're going to go to an out of equilibrium situation where we are going to consider again these two magnets, but now we're going to have one of the magnets point against the effective field. So this is a high energy situation that in principle is in equilibrium would not occur. However, with this spin transfer torque, we can, as I said in the beginning, we can basically counteract dissipation. So we can actually change the sign, effectively change the sign of the dissipation. Meaning that if you pump enough angular momentum from this right reservoir into this right magnet, you can basically overcome Gilbert damping and let the magnet point against the effective field, or against the external field in this case. So this is the magnetic equivalent of putting a ball on top of a hill and then changing the sign of the friction coefficient. So if you push it off from the top of the hill, it will just simply roll back on because it will absorb energy and then go up. Now we consider an antiferromagnetic interlayer exchange interaction. Now, if you look at the dispersion, that is very weak actually. So we only consider it to be to give like we consider it to be very weak. So now we're looking not only at homogeneous excitations, but also at let's say the inhomogeneous excitations. So then you get in the left magnet, which is in equilibrium, you get this parabolic dispersion that Amir also showed this morning. However, in this non-equilibrium situation, you get a inverted parabola for some range of wave vectors. And this is due to the fact that for these small wave vectors, the system actually can lower its energy by making an excitation because it's pointing against the field. So if I tickle it a little bit, it will actually lower its energy. However, it's a stable dynamically, so it's energetically unstable. It's, however, dynamically stable because of the injection of angular momentum. And so that's these states that we refer to as antimagnons. Because they actually carry, because of the reversed direction of magnetization, they carry opposite angular momentum, and they actually also can annihilate with the ordinary magnons. Now, this is maybe mostly a comment for you actually that I put in during the break. So these zero frequency, these negative energy states at zero frequency can be used to create zero frequency edge states out of equilibrium. So this is a specific example of your more general statements that you can only get these zero frequency edge states out of equilibrium. And Peter Gunning, who did this work, is actually in the back. Is your poster about this or? No. Okay. So don't go see his poster, talk to me. No, just kidding, but he can tell you much more about this. Okay, so what I would like to do now is to actually couple these ordinary magnons with these negative energy states. And right now that's not possible because they both have the same gap, so to say. So the height of this zero wave vector low energy excitation is the same as the magnon gap. But if you make the field inhomogeneous, you can increase this and you get a window of frequencies where these magnons and antimagnons couple. And in that window of frequencies, you can have pair creation processes, meaning that if you send in classically a spin wave from the left, it interacts with let's say a negative energy spin wave on the right and creates a negative energy spin wave, but because this negative energy spin wave has angular momentum minus h bar, because of conservation of angular momentum, there have to be two magnons propagating backwards, and this leads to an enhanced reflection that is very reminiscent of superradiance and is related to the Klein paradox. Now, if you do this, if you look at this quantum mechanically, then you basically, and these are now spin current expressions for the spin current that's emitted into the reservoirs, you get a contribution to the spin current that's basically due to spontaneous pair production processes, which is this one here, and that's kind of like, is exactly like a pair production process that is also of the type that Hawking described near black hole horizons, and these magnon pairs that are being emitted at this interface in this non-equilibrium situation are entangled. Okay, here's an advertisement for a conference that you should go to, I hope. Many of you will already be there. It's in a beautiful island in the north of the Netherlands. The weather I'm not making any promises about, but the rest will be nice. And here's my take-home message. So I think these systems, these synthetic antiferromagnets, are very useful for realizing specific implementations of, for example, what was discussed in the previous talk. I gave some examples already, and I think the outlook is to really go to other ways of driving and hopefully also to experiments eventually. Thank you for your attention.